Hello, today we're going to talk about inverse trigonometric functions. Now, there is sort of a problem, and let me outline what the problem is with trying to determine something called an inverse of a trigonometric function. You should recall first that there are two requirements, right? First of all, we might ask, I don't know if you remember what an inverse function is. What is an inverse function? Well, an inverse function is the kind of function where if we have a function where we have y equals f of x, then its inverse function would be written y equals f inverse of x. And the two inverse functions are the kind of functions that if you took the composition of one with the other, so f of f inverse of x would equal f inverse of f of x. And the result of taking that composition would always be x. In other words, they're the kind of functions that undo one another. A really good example of this would be if we had the function y equals natural log of x. You recall that its inverse, y equals e to the x, are inverses of one another, because if we took the natural log of e to the x, the result was x. The two functions undid each other. And if we took e to the natural log of x, it worked the same way. E and natural log of x, those two functions undid one another and left us with x. So an inverse function is this kind of function. What was the requirement? Do you remember this one? What was the requirement for the function to have an inverse? Do you remember? Think about that one for a moment. Well, the answer here is that for the function to have an inverse, it must be 1 to 1. 1 to 1. And the way we defined a 1 to 1 function was that it was the kind of function in which each value of x is assigned exactly one value of y, and each value of y is assigned to one and only one value of x. Our test for a 1 to 1 function was to use if we had the graph, a horizontal line. So let's look at a sine of x and cosine of x. Does it pass the horizontal line test? Well, if it passes the horizontal line test, we'll know, because it will only cross in one place. Each value of y has exactly one value of x. But, well, that's not what's happening here at all, right? Look at y equals sine of x here in purple. You can see there are 1, 2, 3, 4, at least in this picture, and there would be an infinite number of points on this horizontal line where y equals sine of x crossed. It doesn't pass the 1 to 1 test, so it's not 1 to 1. How about cosine of x? Well, we've got the same problem, right? If we look at the cosine of x function, sure enough, right? Multiple points where the y value intersects this horizontal line, just randomly horizontal line, and we see that there are an infinite number of values for cosine of x equal to that value of y. We could even say the same thing about tangent of x, right? Drawing a horizontal line, clearly we don't have a one-to-one function with any of these. So how is it possible? How is it possible for us to get by this particular requirement for functions to be one-to-one in order for us to find an inverse in the first place? Well, the answer to that question is that we limit the domain. It is possible to limit domains and only look at the domains on a limited piece of the function in order to make them one-to-one. So we consider, well, what would we do for sine of x, and how about cosine of x? Well, here it is. This is what we call a principal domain of a sine function. And the way that we limit the domain is specifically to say that as long as we limit the domain to be from negative pi over 2 along the x-axis, and we choose x values that only go as far as positive pi over 2, we've limited it so that it is now the kind of function that is one-to-one. right? This is now 1 to 1 because each value of x will be assigned to only one value of y according to the horizontal line test. So it passes that horizontal line test, and it gives us a good picture of what this function is going to be. How about cosine? Do we go negative pi over 2 to positive pi over 2? Well, the answer here is no as well. In this case, we limit it slightly differently. We start at 0, and we go to pi. Now, why are we choosing these particular values? Well, one of the things that we have to make sure that we do if we're going to limit the domain of a function is that we retain something of the original range. Now, the original range of sine and cosine are both 1 to 1. Negative 1 to positive 1, right? We see that the y values here go from negative 1 all the way to positive 1, and the y values here should go from negative 1 to positive 1 as well. Well, the only way to do that with sine and limit it to be 1 to 1, as well as retain this point that crosses the origin for us, is to make sure that we have a function that stays between negative pi over 2 and positive pi over 2. For cosine, we would have to start at 0 for that kind of thing to happen. So in both cases, we choose these principal domains in order to make sure that we have 0 in that set of y values, and the range goes from negative 1 to positive 1. And so that's our most basic set. One more. How about tangent? What about limiting the domain of tangent? Well, for tangent, the principal domain is going to be very similar to the one for sine. However, in this case, we limit it from negative pi over 2 to positive pi over 2, but we don't include those endpoints, because at negative pi over 2 and positive pi over 2, we have an undefined value for tangent. So if we limit the domain for the principal domain for the tangent function to be between negative pi over 2 and positive pi over 2, we've pretty much covered what we need to. Now, in this case, the range is a little bit different. Whereas for the range of sine and cosine, we went from negative 1 to positive 1. This function continues towards positive infinity, continues towards negative infinity as we approach negative pi over 2 and positive pi over 2. So in this case, the range is all real numbers, negative to positive infinity. And so that's how we limit our range here to make it a 1 to 1 function. All right, more to come.